You ever just watch something and wonder why it happens? Like why a ball always rolls downhill and settles at the bottom. It never just decides to roll back up on its own, right? Well, that super intuitive idea that things always seek their lowest energy state, their most stable spot, that's really the heart of what we're going to talk about today, the thermodynamics of chemical equilibrium.
Because that very same principle applies to chemistry. A chemical reaction is kind of like that ball on a hill. It has a natural tendency to roll in a specific direction, usually from what we call reactants to products, until it finds its own sweet spot, its point of balance. So the big question for us is, how can we possibly predict which way that ball is going to roll? How do we know if a reaction will even happen at all?
Okay, let's get into it. To actually measure that chemical downhill roll, scientists have this incredibly powerful tool called Gibbs free energy. You'll see it written as the symbol delta G. Honestly, you can just think of delta G as a number that tells you exactly how much drive or push a reaction has to move forward. It is the ultimate decider.
And this slide lays it out perfectly. There are really only three possibilities for delta G. So over on the left, if delta G is negative, the reaction is what we call spontaneous. That means the ball rolls downhill all by itself, the reaction just goes. Now in the middle, if delta G is positive, the reaction is non-spontaneous. You'd actually have to push that ball uphill. It is not going to go on its own. And finally, on the right, when delta G is 0, well, the ball has reached the bottom of the well. The system is at equilibrium, and there's just no more energy left to drive the reaction one way or the other.
So that's the basic idea. But in the real world, things are a bit more complicated, A reaction's direction can depend on things like temperature or how many reactants and products you have floating around at that moment. To account for all of that, we need what I like to call the master equation. It's the mathematical engine that really drives all these calculations.
And here it is. Delta G equals delta G naught plus RT times the natural log of Q. Okay, let's break that down because it's not as scary as it looks. That first delta G is the current free energy we just talked about, the push the reaction has right now. The delta G naught, the one with that little circle, that's the standard Gibbs energy. Think of it as a baseline, the reaction score under perfect, standardized lab conditions. R is just a number, the gas constant, and T is the temperature in Kelvin. Together, they kind of set the energy scale for what's happening. And that last piece, Q, the reaction quotient, that's just a snapshot of the ratio of products to reactants at any given moment.
So what's really crucial to get is that this master equation works for the system at any point in time. But what happens when the reaction finally reaches that perfect balance point, that bottom of the well we call equilibrium? Well, this is where the magic really happens.
This slide shows how it all connects beautifully. So, step 1, we start with our master equation. Then, in step 2, we think about what happens at equilibrium. We know two things for sure. First, the driving force, delta G, drops to 0. And second, our snapshot ratio, Q, becomes a special value we call the equilibrium constant, K. Now watch what happens when we plug those into the equation. It simplifies down to 0 equals delta G naught plus RT ln K. And with one simple little rearrangement in step 4, we get this incredible result. Delta G naught equals negative RT ln K. And that's it. That is the direct link between the standard energy of a reaction and where it will end up.
So why is this so mind-blowingly powerful? Because it means that if we can find that standard free energy change, delta G naught, which, by the way, is often a value you can just look up in a textbook, we can literally predict the future of the reaction. We can calculate its equilibrium constant K and know for sure whether we're going to end up with a lot of products or if we'll be left with mostly reactants.
And it's a really simple relationship. As you can see on the left, if your delta G0 is negative, the reaction is spontaneous under standard conditions. And that directly means your equilibrium constant, K, is going to be greater than 1. You'll get lots of products. On the flip side, over on the right, if delta G0 is positive, the reaction is non-spontaneous. That results in a K value that's less than 1, meaning you're going to be left with mostly reactants. Very little product will form. The sign of delta G0 tells you the whole story.
All right, enough with the theory. This relationship is totally a two-way street, and the best way to really feel its power is to put some actual numbers to these concepts. So let's see this thing in action.
Let's give this a try. On the left, we're finding K from delta G. We're looking at the phosphorylation of glucose. That's a key step in how our bodies make energy. Its delta G0 is a positive 13.8 kilojoules per mole. When we plug that into our equation, what do we get? A tiny K value, 3.81 times 10 to the minus 3. Just like we predicted, a positive delta G gives a small k. Now let's go the other way. On the right, for the hydrolysis of sucrose, we start with a known and frankly massive equilibrium constant, 2 times 10 to the 13th. When we solve for delta G, we find it's a big negative number, minus 76,400 joules per mole. A huge K means a very spontaneous reaction. The math just works perfectly.
So let's go ahead and pack our thermodynamics toolkit with what we've learned. We started with the master equation, right? That describes the reaction at any moment. From there, we figured out the crucial equilibrium connection, which links that standard energy directly to the final outcome. The key insight? The sign of delta G star predicts everything about K. And the application is this powerful two-way street, letting us calculate K from delta G star or delta G star from K.
So we now have this incredible ability to predict where a reaction is going to end up. We know if it's going to favor products or reactants. We know if that ball is going to roll to the bottom of the well. But there's one thing we haven't talked about at all. How long does it take for the ball to get there? What actually determines the speed of a reaction? Well, that's a whole other story for another time.